Boolean function optimization methods, namely the Carnot technique and then the Quinn-McCloskey technique. And we have seen how so both of them actually work the same way, except that the steps in Quinn-McCloskey are clearly outlined to facilitate to facilitate a programmable solution. Okay. Yeah, just a second. Yeah, to facilitate a programmable solution. And in both cases, we saw how those are related to performing join operations in the Boolean lattice. Just one aspect that you would have noticed is that the sizes of the cubes actually grow exponentially when you do when you apply either Carnot map or Quinn-McCloskey. So I think you can see my screen. Can you? Oh, okay. All right. Yeah. I think you can see my screen now, right? So if you have noticed that you start with the mean terms, which are cubes of size 1. When you combine them, you get cubes of size 2. When you combine cubes of size 2, you get cubes of size 4, and so on, cubes of size 8. So the sizes of the cubes actually grow exponentially, and this is to be constructed with contrasted with so note that if in the stone construction the sizes of the cubes actually grow linearly with the levels. So there is a difference there. So I mean, although you are performing join operations, but you are not growing level by level. So just to illustrate the situation, let me just draw a diagram. So suppose you have, I'm just saying that suppose you have cubes like this. I mean, let us just say that you got, so suppose you have this 4 cubes. So this will allow you to get, so your let us say the atoms are 1, 2, 3, and 4. So what you'll find, what you can see is that the way it will work is you'll be able to combine them in many ways. Right? Because those are all adjacent. In fact, that is what you are doing. If you remember, you are getting such terms, and then what you are not doing. So that I'm showing in red. What you are not doing. So let me just show in green what you are doing, and what you are not doing. So I'm just putting that. So you are not constructing these intermediate atoms, these intermediate joints, 1, 2, 3. So I mean you can have 4C3 of these. So you are not actually doing this. Rather, what you are doing next is you are constructing these. I mean, let me just put it this way. 1, 2, 3, 4. Then you're also doing 1, 3, 2, 4. You must have seen this sort of. So these are really, so you are doing these also. These you are doing. So I mean, if you just compare it with your stone construction, you are actually jumping through number of levels. So that is one aspect to remember. That's the only thing which wasn't mentioned last time explicitly, although you must have noticed it. All right, so do you have any other questions regarding this, let us say, the Quinn-McCloskey method? Any other questions that you might have? Yeah? All right. I mean, we'll probably look at a few other aspects of Quinn-McCloskey later on, but for now, let us move on to sequential machines. So we are looking at Mealy and Moore machines. So let us just, I mean, we have discussed this initially also. So you're familiar with you're familiar with finite automata, right? You've already studied finite automata, I think. Is that correct?
Yes,
yeah?
sir.
Yeah, well, I think
Yes, sir.
in flat you have studied finite automata. So this Mealy and Moore machines are really just finite automata, but you can say these are variants of finite automata which are more suited to the design and implementation of digital systems. So as usual, you have a finite set of states. You have a designated state called the initial state. That's where the machine starts. So you might have heard of the term initialization. So this initialization simply sets the present state of the machine to the initial state. Okay. Then you have the input alphabet, which is denoted by sigma. You have the output alphabet. There is output alphabet, simply the output of the machine. What is it? Yeah. You have a transition function. So that so this is so when we work with digital machines, we restrict ourselves to just deterministic finite automata. Now I think you are very much aware that non-deterministic and deterministic finite automata both have the same computing power. So is there so if they have the same computing power, so can you just identify a point of difference between finite automata and between deterministic finite automata and non-deterministic finite automata? Can you identify a point of difference between the two, given that, I mean, you have already studied that both of them have the same computing power. Can you identify a difference between the two? Yeah? Anyone? This should be easy actually, it's nothing difficult. Can you identify a difference between the two? Someone can try to answer. Yeah? Pranati, are you there?
Yes, sir.
So can you identify a point of difference between deterministic finite automata and non-deterministic finite automata? I mean, apart from the theoretical, just the definition, we know that we know the definitions of both, but in practical terms.
So non-deterministic automata has more than one initial states.
No, that is not a very important difference because you can always define a single initial step from which you can make non-deterministic transitions to, the other initial state. So that is not a very important difference. Any?
To more than one state.
No, actually, you're missing out in a very important difference between the two. I mean, in fact, that is the reason why people use, people like to use finite automata in. Okay, then let me put the question like this. Why would you, hello?
Hello.
Why would, yes?
Maybe one of the differences that you can be is that for a DFA for a single input string, there can only be one state of one state of existence, but in an NFA for an input, multiple states of existence can be there. Like for
No,
example, if I'm
but that is just related to the definition of I mean just the basic behavior of finite and sorry, deterministic and non-deterministic finite automata. Let me put the question in a different way. Why? No, just let me put the question. I'll just put the question in a different way. Why would you prefer to use a non-deterministic finite automaton instead of a deterministic finite automaton in the first place? Can you answer this question?
The
Why
number
would
of
you?
states are logarithmic of deterministic finite automata.
Yeah, I couldn't hear. So can you
It's
come again?
exponentially more succinct.
Yeah. So compared to NFA, your DFA could have exponentially more number of states, right? So in other words, you can design the machine. So instead of dealing with so many states, I mean, if you consider a situation where that explosion occurs, you are able to design your machine with logarithmically less number of states. All right. So that is really the advantage of a non-deterministic finite automaton over a deterministic finite automaton. That means, the same two machines which behave in the same way, in one case you would have to handle, so many states. In another case, you are able to, get the same behavior, but you got to think of only logarithmically smaller number of states. That's a huge, difference if you think of, you know,
Sir, you are muted.
CRM, you are muted.
Yeah, okay. Yeah, so the two most important components are the transition function and the output function. Of course, all are important because you can't, define the automaton without any one of these, but in operational terms. So when you specify your automaton, these are the two components which you actually specify. The others also you specify. It's not that you don't specify, but these are, easily inferred. These are this transition function and the output functions. These are the two components which which have to be specified, which really characterize your machine. All right, so what you know is that your the basic yeah. So if you think in terms of those, so when you so as I said that you need to specify this transition function and the output function. Let us just look at the symbols of the, yeah, so lambda is the output function. You got to specify the transition function and the output function. So it's usually specified like this. So you have, so how do you characterize the states first of all? So states are characterized by means of state variables. Okay. So you could just call those say is, if you have say 4 states, you could say S0, S1. All right. This could constitute your state, S0 and S1. All right. So if you have 4 states, you could specify those using 2 bits. As such, we can just specify those symbolically using whatever you can say. Probably the choice of S was here was not so good, so maybe I can just call those say Y1, Y0. And you could symbolically, just indicate the states as S1, S2, and so on. You could symbolically, specify the states as S1. So we often make a table like this. So you have the present state. So your, set of states is Q. Of course, if you call it Q, we could call those Q1, Q2, etc. Whatever you like, whatever is suitable. So Q0, Q1, and all those things, or whatever. So whichever is convenient, that is not such a big issue. See, what is important is you have the present state. Okay, you have the present state, and so actually this I can put here. So present state. So present state, let us say it is S1, S2. I have a number of present states. Number of states. Any one of those could be, because the machine will make transitions through those states. All right. And then I have inputs. Okay, I have inputs. So I have, inputs, whatever you like to call. We are calling inputs, you can say. So you have the present state, you have inputs. Okay, so your inputs could be I1, I2, and so on. IM. You can have, so many inputs. So what happens is that you could, so for each input, what do you have? For each input, or let us say, for each input, you can have a new state. So you can have a new state and some is I mean, this is some new state is, I mean, I'm just calling it S11 for the state resulting from S1 on input 1. I can call this I can call this S12, for example, S12 and so on. This is S1M. Then this one is S21, S22, S2M, and so on. So that means I'm in state 2, I get some input on the, as a result of that input, I make a transition to some state. So, you could very well, show it as a graph. Something like that, all right? So, the initial state you mark like this. So let us say this is, I'm just saying this is say S1, S2, S5, something like that. So now I'm getting, so I'm making a transition on input 1, all right? I'm making a transition on input 1. What I've not shown is, so this is the output function. So there are two parts here, okay? So basically I have I, and under I've got, I've got two parts. I've got two parts, let us say. This is really faint. I've got two parts. So one is some say something like Sij. So this is, let us call it Ij. So this is Sij. So I'm making a transition on this input. So on input 1, I go to some state. On input 2, I go to some other state. I mean, I don't always have to go to the different, I don't always have to go to different states. On input 3, also I could go to S2 and so on. So these are some possible. On input 4, I come here and so on. But that is only part of the story. The other part is When I get an input, I also produce an output. All right, I also produce an output. So let us call this Oj. That means I'm in state A, and on getting input J, I produce some output. So that output, let me, call, you know, so I get some output, and so output O, so I have the output alphabet, as you have seen. I have the output alphabet. So these outputs just belong to the output alphabet. So it is O, say, if you put it this way, this is O11. That means output from state 1 on input 1. This is O13. Okay, so output from state 1 on input 3. This is O12. So on. So these are just, so that is how I specify the machine. Okay, that is how I specify the machine. This is on input 4. All right. So this is how I can specify the machine. So here I will, usually write O11, O12, and so on. O1N, O21, So on each input, so what do you see in this table? So this one is input slash output. Okay, so in other words, this part is specifying delta. This part is specifying delta. All these are specifying your delta, and in blue, all these are specifying your lambda. All right, these are in blue I am specifying an output function, and in this orange I am specifying your transition function. So first of all, this should be clear to you. What we are specifying here. So this is your, so these are your often called next states. These are often called your next states. So you have your next state, and here you have your output. All right, next state and your output. So this is your table which indicates both your transition function, which is, or you can say the next state function. So these are typically called, you say, you usually call this the next state function. And the output function. Okay, so these are the two functions which you need to characterize your finite state machine. Okay, these two together make up your FSM. So is this clear to you? Any questions here? Yeah, regarding the specification of the FSM. So when your machine may be fully specified or incompletely specified. So fully specified simply means that for each input you know what your next state is going to be, what your output is going to be. Okay, you are specifying it fully. Sometimes you don't specify it fully, sometimes you don't care. Okay, just as you have seen that for your for your uh, optimization, your two-level function optimization, sometimes you don't need to for certain inputs you don't need to clearly specify your output. So that means certain mean terms can be either in the onset or offset. You don't really care. Those are don't cares. All right. So similarly, for a finite state machine, some of the entries in the table could be left unspecified because those could be, don't care entries. So a table where some of the entries are don't care entries are the that represents an incompletely specified machine. On the other hand, if all the entries in the table are specified, then you have a fully specified finite state machine. All right, you have a fully specified finite state machine. Now, so what you see is that always you are having, see, when you have this transition, you are changing your present state. From your present state, you are making a transition to a new state. All right, you're making a transition to a new state. So that you could visualize as follows. So how could you consider your present state? So suppose you think of your present state, as you have seen, you have a number of state variables. Okay, you have a number of state variables. So let us say that you have, say, these are your state variables. All right. So this constitutes your present state. The state variables, these constitute your present state. So you can use the values of the state variables, right? You can use the values. So you have or if you like, I can maybe I can. So this is your transition function, and this is your output function. So your state variables are going to both the places. It's going to the transition function. It's also coming here. So this one is going here. It's also coming here. All right. So all of these are going here, coming here. All right. So these are your outputs. All right. These are your outputs. And here what you get is your delta is computing your next state. So this is y0 dash. This is your next state. This is y1 dash. This is y2 dash. This is y3 dash. So these are your next state, and these are your outputs. Okay, these are your outputs, but what I have not shown as yet are your inputs. So let me show the inputs in some other color. So you also have your inputs. Okay, so you also have your inputs coming here. Let me just draw it. Sorry. These are your inputs. Alright, so you have your inputs. So as you can see, your your output function is computing the outputs using the present state and the inputs, and your next state function is computing the next state based on the present state and the inputs. So this kind of a machine is called a Mealy machine. This kind of a machine is called a Mealy machine. All right. And in case, okay, so are you clear about a Mealy machine? What this Mealy machine does? So as you can see, okay, these are called your, these are often, so these are, storing your present state, and these are often called D flip-flops. These are often called D flip-flops, okay? So these D flip-flops, they just store your present state, and in case of a synchronous machine, you have a clock. You have a clock. So your clock is basically a train of pulses, all right? Your clock is a train of pulses. So these, flip-flops are usually, these are either positively, these are triggered at the positive edge or at the negative edge of the clock. It depends on the design of your flip-flop. So what happens is either at the positive edge or at the, or you can say the rising edge. So this is called the positive, or simply rising edge, and this is called the negative or falling edge of the clock. Okay. Okay. So it's either, you can call it the falling edge or the negative edge of the clock, and this is the positive or the rising edge of the clock. So your flip-flop usually, this will transfer. So the flip-flops usually transfer. So this is the input of the flip-flop, this is the output of the flip-flop. So this flip-flops usually transfer the data at the input, to its storage, either at the positive edge or at the negative edge of the clock. Okay, so that's so these are called D flip-flops or data flip-flops. Okay, these are called D flip-flops or data flip-flops. So these flip-flops, as you can see, these are the heart of a finite state machine, because these are the states of the machine. These are the state bits of the machine. And the rest, these are combinational circuits. Okay, so these are combinational circuits. And this is also a combinational circuit. Okay, so these are combinational circuits, and these are your state variables, these are your flip-flops. So as you can see, your finite state machine has combinational circuits to compute the output function and the next state function, and it also has state variables to store the present state. Okay, and in case of a Mealy machine, the output depends on the present state and also on the inputs. Now, in case of a Moore machine, you don't have this. It depends. In case of a Moore machine, your outputs depend only on the present state. They don't depend on the inputs. So that's the difference between a Moore machine and a Mealy machine. So in case of a Moore machine, your outputs depend only on the present state. That's right. So in case of a Moore machine, your outputs depend only on the present state. In case of a Mealy machine, your outputs depend on the present state and also on the inputs. Okay, so that's the difference between a Mealy machine and a Moore machine. So is the notion of a Mealy machine and a Moore machine clear to you? Any questions there? Yeah? No, say something. Yes?
No, sir.
All right. So these are called synchronous machines. When the state transition occurs under the influence of a clock at either the rising edge or the falling edge of a clock, then you have a synchronous machine. So both Mealy machines and Moore machines, these are synchronous machines. All right, both of these are called synchronous machines. So why are these synchronous? Because they work under the influence of a clock. So simply these are clocked machines. These are clocked FSMs. All right. So the synchronous machines are very simply, these are clocked FSMs. The operation of synchronous machines, either Moore machine or Milli machine, happens under the influence of a clock. All right. So now, in this context, it's often good to talk about a Huffman machine model. All right. So in case of a Huffman machine model, you can think of a combinational cloud. Combinational cloud. All right, and you have your state variables. All right, and then you have I think someone might something is going. Are you able to hear?
Yes, sir.
Yes, sir, we can hear you.
Oh. Yeah. So this is Huffman machine model. Okay. Of sequential machine. Now these are called. This is the primary input. This is the primary output. This is a secondary. This is the secondary input. All right. So this is your Huffman machine model of a sequential machine. So as you can see, you have primary inputs coming in here. You have the primary output, and so primary input is basically your coming from sigma. Primary output, this is your delta. This is your input. Primary inputs come from your input alphabet. Primary outputs come from your output alphabet, and then you have this secondary input. Secondary inputs, these are your really your state variables. Okay, so secondary input, this is really your present state, isn't it? Secondary input, and secondary output, this is your next state. So just it is useful to have this notion of a finite state machine. So, and this is the Huffman model of a finite state machine. So I think at this point we'll just so I hope I mean, these are your very, this is just about the structure, very, a high level structure of finite state machine, a sequential machine. In particular, these are, this is, I should say, a synchronous. So it is also important to say that there is a clock over here. Okay, there is a clock over here. So that is what makes it synchronous. And the clocks work only on the state variable.
Sir, you are muted.
All right. Okay, so this is all for today. We'll continue. So I think next week is, you don't have classes next week, right? Hello?
Yes, the next week is vacation.
Part of it.
Oh, so, all right. Yeah. Okay. I think we'll just refer to the dates. Pavitra, are you there? All right. We'll just refer to the dates. I think at some point you are going to have your study leave or something. Yeah. All right. So we'll continue from the next class. Okay. We'll stop here.